The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
So I'm going to talk about three projects, and I'm going to try to give a little bit of background about each one. I'm not going to be able to get into too much detail about each one, but I wanted to focus on some of the material characteristics of each one given the nature of the session here. Trump Tower, it's right in our backyard in Chicago, and then two projects that I had the fortune of working on that are located in Dubai. I'll start out with Trump. Incidentally, Trump Tower is one of the three projects that I did not work on directly. It happens to be in our own backyard. But the nice thing about this collection of these three projects, and the reason why I grouped them together, is because there was a lot of overlap in terms of the design phase in our Chicago office. At certain times, all these projects were kind of going on together, and there was a lot of information sharing. So the Burj Khalifa team was, talking with the Trump Tower team, and so although I wasn't directly involved with Trump, there's a lot of similarities that I think you'll see in terms of the materials. The Trump Tower site is a fairly prominent site. It happens to be located on a part of the Chicago River that, as the river makes a turn towards the east, there's a little jog in the river, and it creates some interesting characteristics. If you're standing on Wabash, which is right here, you can look up Wabash North, and you can get basically like a broadside view of Trump Tower, which is kind of unique. And then also, if you have the fortune of owning a residence there in Trump or staying in a hotel, you can, in some areas, look down like completely uninhibited view down the river towards the lake to the east. And it does have some famous neighbors. There's the Wrigley building just to the east of Trump Tower, and the IBM building, a Mies van der Rohe building just to the west. And then further off to the west is the Marina Towers, which Larry touched on, which I believe at one point they were the world's tallest concrete buildings, although I think it was a short period of time. Just to get a sense of where Trump is in terms of the Chicago skyline, basically it's the city's second tallest building when measured by roof height, which is something that we like to do in Chicago because it elevates Sears in the sort of the global scale of things. And this is where it would land in the lineup sort of the world's tallest buildings again. Based on roof height, you see it's right next to the John Hancock Tower there in the middle. 1,133 feet tall. It's certainly a mixed-use development with about 2.6 million gross square feet, predominantly private condominiums in the top two-thirds, and then a hotel in the bottom third and some retail space at the bottom of the building. Structural system is entirely cast-in-place reinforced concrete, as are all the three projects that I'm going to present here today. Central reinforced concrete core wall, flat plate slab system and columns, and we're utilizing outriggers to tie the perimeter column system with the core. Now, how we used high strength, and I'm saying high performance concrete, and the reason I'm saying that is because it's not always just about the strength, although that is certainly a big component of why you want to achieve higher goals with your concrete. But oftentimes there's other things that come along with the strength that are intentional, such as stiffness. We've talked about that a lot in this session. But other things like increased durability with reduced permeability are other factors. And then also there are some cases where we're going to utilize self-consolidating concrete. So there's sort of a family of characteristics, strength being one of them, but these other performance characteristics are very important. So for Trump, for the mat foundation, we used 10,000 psi concrete, self-consolidating. And then for selected slabs, typically in the outriggers, associated with the outrigger zones, we went up to 12,000 psi. And in some of the vertical columns and walls, we ranged between 8 to 12,000 psi. And the outrigger zones were certainly the highest. We went up to 16,000 psi with those, coupled with the self-consolidating concrete characteristics. I talked about the outriggers. The outrigger systems are difficult to deal with. Sometimes you have abrupt changes in stiffness, which attract a high degree of load, but they do have certain undeniable functional advantages for buildings, and so oftentimes they're utilized for tall buildings. They're creating a large change in stiffness, as I mentioned, as they're trying to dump load from the core and engage the outer perimeter columns. And these are some details of what our outriggers look like. We have two conditions where we have reinforced concrete outrigger and then the addition of structural steel plates where the loads get significantly high. And you can see the type of scale we're talking about, 17 feet deep by about 5 foot 6 inch wide. The reinforcement ratios were fairly high, which was certainly the reason why we wanted to go with self-consolidating concrete along with the high strength. So some details about the mixed design for the special outrigger zones. 16,000 psi was specified at 90 days. self-consolidating concrete, and you see kind of the main ingredients of the mix: Portland cement with fly ash and slag cement replacement. Microsilica was also used, and then we have a high-range water-reducing admixture coupled with a viscosity-modifying admixture to stabilize the mix for the self-consolidating concrete. So anytime we have self-consolidating concrete, you'll see that there's a common theme here where we're coupling the viscosity modifier with the water reducer. And the max aggregate size for these zones was 12 millimeters. Water cement ratio, pretty low, 0.22 to 0.25. We did some pre-construction testing of this mix because of the somewhat exotic nature of the mix. We saw that at 90 days we were up at about 18,000 psi, at least for the cylinders, and we got a static modulus at 90 days of about 7,300 ksi. The density came in at about 153 pounds per cubic foot. These are some images of the reinforcement here. This is the lowest outrigger level. Here's a case where we've got embedded steel plates to kind of deal with some of the strut and tie forces that we were seeing in the outriggers. And you can see the amount of congestion here. We've got rebar couplers in place of lap splices. The lap splices just wouldn't fly in these types of situations. But you can understand why we've gone with self-consolidating when you look at some of these images of the amount of congestion that we have in these high-stress zones. Okay, I want to move on to the mat foundation here. We're targeting 10,000 psi concrete for the mat at 56 days. Modulus, fairly moderate modulus of 6,000 ksi at 56 days. And then we also specified, because of the mass concrete nature of this element, we specified an 80-degree Fahrenheit max concrete temperature at delivery with 170 max concrete temperature in place. And then also, very important, the differential stress between the core zone of the mat and the surface. That's something that is perhaps maybe even more important, as we don't want to develop residual stresses as things cool differentially. And we did utilize self-consolidating concrete so that there was no vibration required for such a large tub of concrete. Some of the stats on the concrete mix for the 10,000 mix: self-consolidating, as I mentioned, Portland cement, and then the usual suspects here that you'll see as a recurring theme: fly ash and slag cement replacement, microsilica certainly. Here we have a type D chemical retarder, again, to try to control that differential thermal gain in the mass concrete. And then a high-range water-reducing admixture, again, coupled with a viscosity modifier to stabilize the mix and avoid segregation. Max aggregate size was bumped up a little bit. We've got a blend of a 12 and 19 millimeter crushed limestone. And water cement ratio jumps a little bit from what we saw in the outrigger zones, 0.26, 0.28, still relatively low. This was the mat foundation, about 200 foot by 60 by 10 foot deep, 4,500 cubic yards poured basically over a 24-hour period using 3 conveyor belt systems. And we did thermocouple the mat in a number of locations, and this is the temperature trace, and you can see from, in the middle of the core of the mat to the top and bottom surfaces, we're trying to monitor that differential temperature, which is quite important. Moving on, the next kind of location where we're targeting high strength, high performance was in the vertical elements and select slabs, where we were targeting upwards of 12,000 psi concrete, again specified at 90 days. It wasn't a self-consolidating mix, but it was certainly a high slump concrete, high flow. So you can see we've got the high range water reducing admixture. In this case, we don't have a viscosity modifier because the flow wasn't nearly as high as the outrigger zones where we had self-consolidating. So it wasn't as necessary to do that to maintain the stability. But still a generally low water to cement ratio, and here we have a slump of about 7.5 inches, plus or minus 1. I know this has been mentioned a couple times in the session, but you do sort of question, what you're getting out of a slump specification. When things were simpler, where you had Portland cement, water, and fine and coarse aggregate, the slump told you a lot about consistency of the mix and what you were getting. But when you have all these admixtures and things here, I think it loses a little bit of what, as a benchmark that it's used to sort of gauge the consistency of your concrete. Some data of the strength reports for the 12,000 psi mix. We were testing out at about upwards of 13,500 or so for the average strength at about 90 days. And just to close out on Trump, at least, some images of the construction here. The image on the left is the one that I mentioned earlier. We were standing on Wabash looking straight north. That's basically just outside the back door of our office. And this is the view from Lake Michigan. So it's certainly become an iconic feature of Chicago's skyline. It's nice to see something be deposited in the Chicago skyline recently to kind of bring it to a more contemporary feel to the skyline. Okay, I'm going to move on to a unique project in Dubai that I had the good fortune of being able to work on, not only in the design but also on site. I think the official name now is Cayenne Tower. They're the developer and our client. We called it Infinity Tower throughout the design, so you'll see a mix of terminology here. I think they wanted a little bit more distinct name because if you Google Infinity Tower, there's a few out there right now that sort of claim to call themselves Infinity, so they wanted to separate themselves. But it is the world's tallest twisting tower. It twists 90 degrees from the base to the top of the building. And what would seem somewhat of a whimsical idea, to take a tower and twist it, I have to admit that there's really no, and I don't think any of you would be surprised by this in this room, there's really no structural motivation to do such a thing. But there certainly is an architectural story behind it, and that story is that the site is quite unique in that it's right at the inlet of the Gulf to the marina in Dubai. And because of that, there's a difference in the views that you're trying to sell, whether you're in the lower part of the building or the upper part of the building. So the idea was that in the lower part of the building where you don't have the vantage point out to the Gulf, we're really trying to take advantage of the views right into the marina and kind of the life in the marina there. But as you got higher up in the building and you could really take advantage of the views out to the Gulf, the predominant kind of view direction to the tower changes, and that's kind of the selling point of these residential units. And that's what's trying to be depicted here in this image. Now, I can probably do another half hour on why we arrived at the way that we dealt with the twist on this building, but I'm just going to touch on it here just because that's not really the intent of this presentation. But the structure itself doesn't necessarily just twist along with the form of the building. What happens is the columns undergo a series of kind of steps to the side and then lean. We looked at advantages and disadvantages of doing a number of different things, and this was sort of thought of as like a middle ground in terms of constructability and what it provided for units, the residential units. And so I'd say it was a compromise, but the reason I'm bringing it up is because the stepped nature of these columns created a situation where we had some high rebar congestion, because essentially what you have is a continuous series of column transfers from the top of the building to the bottom. And I'll talk about why that's important here, and you'll see some images, and I'll come back to that. But just to give you a sense of the overall structural system, entirely reinforced concrete cast in place. There's a perimeter central circular core that's consistent up in the middle of the building, and then there's a reinforced concrete moment frame around the perimeter that actually creates the twist. And the floor slabs are a flat plate construction. Foundations are pile-supported mat foundation, fairly conventional. For Infinity Tower, the idea or the motivation to do high-strength, high-performance concrete was for a couple of reasons. Certainly, we wanted the high strength and low water cement ratio for kind of the structural advantage of keeping members small as possible to maximize the amount of sellable area. We also were looking at trying to achieve reduced permeability for the below-grade applications because the chlorides and sulfates in the ground in Dubai are pretty extreme. And then you'll see in some of my construction photos, we've got quite a bit of congestion in some zones, certainly at the lower part of the building. And so we wanted to maximize the ease of placement and improve the flow characteristics of the project. And that was really, I had the opportunity to be out there for a number of the concrete pours. That was by far the number one key to the success of this project, was the quality of the concrete that was placed given the amount of congestion that was there for the reinforcement. And then we specified higher modulus of elasticity in order to control the amount of not only wind drift, which is normal on a building, but also gravity drift, because this building is somewhat fighting its own weight because of the twisting geometry of the tower. Some of the concrete material properties, I'll skip right to the imperial units for the metrically challenged here. But from the foundation to about level 50, we had about 10,000 PSI concrete. Not totally exotic, but certainly for Dubai. You can't do in Dubai what you can do in the U.S. all the time. So this is certainly a little bit of pushing the envelope, at least at the time, for what could be done in Dubai. And then we tailed it off to about 7,000 PSI concrete in the upper kind of third of the building. And we did specify modules of elasticity at 90 days, which was quite challenging actually for the ready-mix guys to achieve. We had a lot of back and forth on that one. I'll talk about that in a little bit as well. Some of the mixed design characteristics, the perimeter moment frame was self-consolidating concrete from the bottom of the building to the top of the building. We specified, if you remember from the previous slide, 70 MPa cylinder strength. They had to bump it up to about 75 to achieve the modulus that we required. In fact, I think they probably snuck it up a little bit beyond that as well. It was a kind of what they call a bi-mix, which is a Portland cement with a fly ash replacement, silica fume, and a super plasticizer, again with the viscosity modifying admixture to stabilize the mix. Max aggregate size was bumped down to 3/8 of an inch, again to kind of enhance the placement and the pumping of the concrete. The core walls, the central core walls, were a bit of a unique thing. They actually slip formed the core walls. They actually had slip forming technology out there, and they were advancing the core walls through slip forming, and they were going way ahead of the rest of the tower. We actually had to tell them they had to put the brakes on after a while because they were just going way beyond what they were able to keep up with the rest of the frame. But the slip form, because they were using slip form, it wasn't a self-consolidating mix because you need a certain amount of early age strength to do the slip forming. But it was a high flow mix, 70 MPa cylinder strength, about 10,000 PSI. Again, this bi-mix, which you've got fly ash and Portland cement together, microsilica and a super plasticizer, no viscosity modifier here in this case. And we bumped up the max aggregate size to 20 millimeters. This is kind of interesting. Just to give you an idea, I mentioned the fact that they were having trouble achieving the modulus elasticity that we specified. I plotted here the relationship from ACI modulus elasticity relative to concrete strength for normal strength concrete and then for high strength concrete. And then I plotted a 20% offset, which is sort of thought of as maybe the acceptable range of what you might get out of tests relative to that equation. And you can see what we specified at C70 was kind of even beyond the increase in 20% on what you'd expect from the modulus elasticity. And it does have to do with the aggregate. We've talked about that a number of times in this session. And you know, in Dubai, they're using kind of a crushed limestone, maybe not quite as good as a coarse aggregate as what you might find in other parts of the world. And so they had to move that strength over to the right there to try to get back to within the range that they could achieve with the modulus elasticity. But it certainly wasn't easy. It was a big struggle on this project, actually. Okay, a little bit about the congestion. I talked about the stepped column situation. We knew that there was going to be high reinforcement congestion. It wasn't a surprise. In fact, we did a lot of 3D drawing of these joints and laying out all the rebar so that we can convince ourselves that there was something that's actually constructible and plan how you would do this. And so we drew details of all these joints with the reinforcement in there. We used a lot of rebar terminators instead of hooks. We used a lot of rebar couplers instead of lap splices. Lenton and those people loved us on this project. But I wanted to show this because this was a joint at this corner of the building. You've got your column bars coming up, and then you've got the perimeter moment frame beams coming in from two sides. That column was about 6% reinforcement, and you can imagine the amount of congestion here in these zones. And we had a lot of effort to try to coordinate where the terminators were and plan where the terminators and the couplers were. And the self-consolidating concrete, like I said, the quality on the finished concrete was unbelievable. Given the congestion of the reinforcement, this was kind of the finished product for some of those stepped columns there. Really, really good quality of concrete placement. Some views. You get some pretty unique images of this project given the geometry of it. So this is looking straight on from the other side of the marina. One other thing that we were really kind of interested in this project because of the fact that it was quite unique in the sense that the self-weight of the structure was sort of forcing additional twist displacement on the structure. We wanted to make sure that we monitored the movement of this thing over time, partly because we wanted to help the contractor, because we had specified that they needed to keep basically truing up the tower back to the theoretical coordinates at every level. And so they really needed to know where they were so they could understand what kind of corrections to make. And it's sort of an education process we needed to walk through with them and implement this surveying program. But this is the kind of data we got out of it. And this was kind of nice to see. This was taken at a corner column at level 55, and you can see that as additional load is placed above level 55 and you got the early strength concrete, you do get additional sort of twist movement in the building. But then it tails off nicely. And this is what we want to see. We want to see this plateau. It's certainly going to be a little bit unsettling if we don't see this plateau. And the red dot was our predicted data point for this particular column based on our creep and shrinkage and construction sequence analysis that we did. And some construction images. I'm going to walk you through. This is as it's taking off. The core ended up getting about 15 floors or so ahead of the rest of the tower. And one of the things that concerns us when you do that is that the core is going to sort of free creep, and then you're going to have alignment problems when you try to bring the slabs up to the core, and you're going to have dowel misalignment issues and things. So we had to put the brakes on the slip forming. So the slip forming technology stayed in place, but they sort of used it eventually as sort of a jump forming approach. There's some views of the odd geometry and perspectives that you get looking at the tower. And here I'm calling it Cayenne. That's more appropriate, as that's its official name now. It really is, despite all the headaches that it gave us as engineers in the design process, it really is kind of a stunning building in the marina. And I don't know, this is just recently, I think a couple days ago, this French guy that calls himself Spider-Man actually climbed it. So I don't think he cares anything about what I've been talking about, but I think he was probably pretty concerned that the perforated metal panels that he was using to climb stayed on the building. Okay, Burj Khalifa, I'm going to close out with this one. I had the good fortune of working with this one early on in my career. I worked with Larry. I learned an awful lot from Larry on this particular project. There's a wealth of information here. I'll try to distill it down just to the material characteristics, but just to give you a sense of, I thought this was kind of interesting because this is the holders of the title of world's tallest over a 100-year span. And it just kind of goes to show you that there was this sort of trend that was started. And then it sort of plateaued off at the end of the 20th century with people haggling about, was it top of spire, top of antenna? And what's nice about this is it seems to sort of like carry on that trend that was started back in the 70s or so. So Burj Khalifa, once again, is an entirely cast-in-place reinforced concrete structure. There is a portion of the top of the tower that is structural steel, but it's relatively small amount of area compared to the rest of the building. But it has a pretty straightforward structure, actually. It's pretty similar to what John showed for Kingdom Tower, where everything's fairly well directly connected. The system is fairly straightforward to explain to people in the sense that you have a torsionally closed central box, which gives it some torsional stiffness. You've got a lot of shear stiffness through the longitudinal walls, and then you've got flexural stiffness at the ends and sort of the flange walls, or what we call them as the hammerhead walls. And I plotted this. This is a plot of building height with building materials over time, and I just cut it off after a certain height, which is why you don't see a lot of data points low down in the building. There's a lot of things going on here, but just to touch on kind of the most pertinent one, which is that Burj Khalifa is the red triangle up here, which for an entirely reinforced concrete building was a significant departure from the trends that had happened kind of in the late 1990s, early 2000s with using a lot of composite structures. So it really stands apart from kind of the rest of its peers in terms of that it was entirely reinforced concrete. To give you an idea of some of the materials that we used on Burj, the max concrete strength that we used was about 9,300 psi, as Larry mentioned earlier. That was at 56 days. And then we tailed that off as you go up toward the top of the building, but we did also, again, specify a minimum modulus of elasticity, which was necessary in terms of controlling the strength of the building and the occupant perception of certainly the upper residential areas. Now, again, 9,300 psi isn't extremely exotic. It's certainly not 16,000 psi, but again, for Dubai, for that time, it is on kind of the upper end. Now you can probably push it a little bit. Kingdom Tower was using 12,000 psi concrete, but it goes back to your local materials that you have available. So for the superstructure concrete, it was a high flow mix. It was called near self-consolidating concrete, 80 MPa cube. Again, it was another one of these what they call bi-mix, which is fly ash and Portland cement, supplemented with microsilica for strength, also for lower permeability, and then a high-range water-reducing admixture with a maximum aggregate size of 20 and 10 millimeter blend, water-to-cement ratio target of about 0.3. So again, you don't see the viscosity modifier because although it was a high flow, it was not self-consolidating concrete. Here's some images of the construction. You don't see the puddling here because these kind of column-like or wall-like elements advanced ahead, and then we doweled in, so there was no issue about puddling or discontinuity of the higher strength concrete in the vertical elements. And I like to show this image because it's not often that we get a chance to see such a large section of a building exposed for the structure. There was a little bit of a hiccup with the cladding contractor, and so it afforded us the ability to take some photos that have completely uninhibited views of the concrete frame for a number of stories. Another thing that was quite unique about Burj Khalifa was that they had to prove that they could actually pump the C80 concrete over 600 meters in the air. So what they did was, in order to approximate the amount of hydraulic losses that they anticipated going vertically, they laid piping down horizontally and proved to themselves that they could actually pump 9,300 psi concrete single stage to over 600 meters, and they did that. Moving on to the mat foundation. Mat foundation, we did use self-consolidating concrete, similar to Trump Tower. We had about 6,000 psi cylinder strength at 28 days. Portland cement fly ash mix with microsilica once again, and you see the water-reducing admixture in combination with a viscosity modifier for the self-consolidating characteristic. And we used, similar to Trump, a water-reducing admixture type D, and also a corrosion-inhibiting admixture based, calcium nitrate based, because of the corrosive nature of the ground in Dubai, and a water-to-cement ratio target of about 0.3 to 0.38. Again, we're concerned about maximum temperature at placement, maximum temperature gain overall, and then what I don't have here, which certainly one thing we were keeping an eye on, was the differential through the thickness. Pile supported mat foundation, fairly straightforward, about 3.7 meters thick, I believe, and 1.5 meter diameter cast-in-place piles going about 50 meters deep. And we also further kind of helped the situation by providing a cathodic protection system for the foundations as well. We did test cubes. These are actually images of the real mat foundation where we use controlled permeability formwork, which in combination with the microsilica and the low water cement ratio really minimize the permeability of the surfaces of this concrete. So it's this really high quality, low permeability mix to cut down on the amount of intrusion of corrosive elements. Some images in the upper left there, those are the test cubes that we constructed and thermocoupled to make sure that the contractor had a strategy to control the max temperature gain and the differential. And then what seems a little bit counterintuitive, we actually insulated the top surface in order to further control that temperature differential. It seems like you'd want to expel as much as you could to limit the total thermal gain, but then you've got a problem with differential. And we poured this mat in 4 stages, each of the 3 wings, and then came back with the center portion to kind of limit the amount of restraint that the mat created itself as it was drying and curing. Here's some images of the pile-supported mat foundation under construction. And then self-consolidating concrete basically filling up like a bathtub there. And I didn't have Kansas City, but I did put Burj Khalifa in the Chicago skyline, which is fairly close, and this is what it would look like. So in summary, I think high-strength, high-performance concrete is absolutely essential for any tall and certainly super tall tower projects, not only from a standpoint of its strength, trying to minimize the size and maximize the sellable area, but also from stiffness, from a performance standpoint, and ease of placement. We often get into cases where we've got, although we'd like to avoid it, high rebar congestion. Integrity of the concrete because of the fact that it places well in congestion, and then increased durability. These are all factors that, in addition to strength, come into play with high-performance concrete in super tall towers. Thank you.